In the last lecture, we started thinking about data sets, collections of values that represent numbers from a collection of subjects. And how do we characterize that information? How do we describe it? The main tools that we talked about were mean, median, mode, but we also introduced the idea of a histogram and the shape of a distribution. And the last thing we got to was thinking about how wide or spread out the distribution is. And that's our focus today. What are the measures of the variation within a distribution of data? So this is where the link will be to this voiceover narration, which does not exist yet. All right, so why does variation matter? We can describe the measure of center. Why do we care about that? Well, the measure of center will tell you what's common or likely or a typical value. Hopefully you got a sense of why that's important in the last lecture. But it's a way of summarizing what the data set is telling you. Right now, if you only have a few values, maybe these numbers aren't that important. But what if you have data sets of hundreds or thousands or millions of points? Well, you need to summarize it in some way, and the measure of center is a way to do that. But it doesn't give you information about what it means for a randomly selected individual, right? Or it doesn't give you that much information. It's one number that's representing the full data set. What you'd like to know is how likely is an individual to be near that center, right? So if I tell you the average is X, well, what do you do with that information, right? Are you near that number? Is a typical person near that number? How likely is it that any individual that's part of the population would be near that measure of center? That's what the variation is telling you. And so you get a much more complete picture if you give the measure of center and also the measure of variation. Because that can tell you how likely you are to be near whatever that center value is. So let's take a look at an example here that illustrates how variation can actually make a real difference. We have two banks, and the histogram that's shown here is for their waiting time. Now this one is a much flatter distribution. This one is sharply peaked. They have the same mean value, so they would be represented by the same measure of center. But obviously the variation is very different. So which one would you prefer? This question does not have a right answer. I have an answer for myself. You might have a different answer, but my answer would be this one. I'd probably prefer this one because I have more certainty about when I visit the bank, how long it's going to take me to get my business done. Whereas in this one, yeah, I might get in and out of there quicker, right? There's a reasonable chance I'll get in and out in 4 minutes, but there's also a reasonable chance I'll get in and out in 11 minutes. And so the variation here is a lot wider compared to over here where the variation is very small. The simplest measurement of variation is the range. You take the highest value and the lowest value and look at the difference between them. As a quick estimate, that's fine, but simplest isn't always the best. The range is very susceptible to outliers, even more so than the average, right? The average considers all of the values, adds them up, divides by the sample size. The range literally only takes the highest and lowest value. So if there are outliers on both ends, the range will be completely determined by outliers. So the range can be a very misleading measurement of the variation. So let's take an example here. Consider the range in daily snowfall in Florida. There's very rarely snow, but it does happen occasionally. So the measurement of center might say that the daily snowfall in Florida is basically 0, but the range might be 0 to 4 inches just because of just one time that it snowed 4 inches. So range is not the best way to measure the variation in a data set. A better way is through quartiles and the 5-number summary. And the main tool here is a box plot. We'll get to that in a second. But what you do is you take the data set, you divide it into percentile markers, as written here, and that gives you 5 values. So quartiles, that means there's 4 ranges, and those 4 ranges are defined by 5 numbers, right? So the lowest value, that would be the 0 percentile, then the lower quartile is 25%, median at 50%, upper quartile at 75%, highest value at 100%. So these 5 values divide the data set into 4 quadrants or quartiles. Okay, what these numbers here represent, the lowest quartile number, for example, is 25th percentile. So 25% of all the data is below the lower quartile. 50% is below the median. 75% is below the upper quartile. 100% is below the highest value, obviously. So we can represent these numbers, these 5 numbers, in what's called a box plot. And here are box plots for the waiting time in the previous example. So the lower one, this was the waiting time distribution on the left, where it has a range. It goes from 4.1 minutes up to 11.0. The median value is 7.2, and the middle 50% spans from 5.6 to 8.5. So visually looking at the box plot, you have a line for each, a small little vertical line here, for each of the 5 numbers in the 5-number summary. And all 5 numbers are written on this box plot. So this is the 75th percentile, the upper quartile value. And we can compare it to the box plot for the other bank and see its 5-number summary. The 5 lines representing that 5-number summary, the box around the middle 50% of data, and the line at the median. Their median lines match up, but the boxes are way smaller, so we can immediately see the difference in variation between the two distributions of data. So box plots are useful tools for that. In the example video, when you click on the folder for examples, there's a video there looking at a data set. I show how to make a box plot in Excel, and also the other measurements of variation that we're going to talk about briefly. Okay, so this is the breakdown of the previous graph in more detail. And you can see the 5-number summary is all labeled out. The box in the middle represents the middle 50% of value. And this just repeats what I said before. The percentile represents the percentage of data that is below that value. So the 5-number summary, these are numbers that are in the data set. And they are the numbers that correspond to what these percentiles are. All right. So we would use the 5-number summary, we'd use box plots when our measure of center is the median. When that's the appropriate measure of center, box plot is probably a good tool, 5-number summary is a good tool. But what if your measure of center is the average? Then we're not thinking about things in terms of percentiles necessarily. In that case, the common way to describe the variation is through the standard deviation. And the standard deviation has a complicated formula, although having done the finance formulas, this is no more challenging than that. But what it's representing essentially is the average difference from the mean. So on average, how much do values vary from the mean? And I want to explain a little bit about where this formula comes from, because it is complicated looking, and you might think, well, why does it have to be so complicated? Well, look at what's in parentheses here, x minus x bar. So a value in the data set minus the mean value, the average value. That's the deviation of each value from the mean, so how far away it is. So let's say the mean was 5, and I pick out a value and it has a value of 10. then 10 minus 5 is 5. The deviation is 5. Now let's say I pick out another value and it's 0. 0 minus 5 is minus 5, so it has a deviation of minus 5. Okay, so any value in a data set will have some deviation from the mean, and that is a representation of how much it varies from the mean. But the mean is essentially like the middle point, and if you just added up all the deviations, it would sum to about 0, or close to it, because you'd have some deviations that are positive and some that are negative. So we can't just add up all the deviations. And so a way around that is we can square them, and then we're not really caring about whether it's a positive deviation or a negative deviation. It gets squared, and by squaring it, all of these values are positive, and then you add them all up. Okay, so you add up all the squared deviations, and that explains why we need to square root at the end, because we want the standard deviation to be kind of in the same units as the values of the variable. So if we're squaring them here, we have to then square root them so the units come back to be the same. And then in the denominator, we're dividing by n minus 1. The minus 1 part would take a longer time to explain, having to do with something called degrees of freedom and kind of technical details that you don't really need to know unless you're really interested. But the n part should make some sense, because what we're looking for is the average deviation difference from the mean. So we take these deviations and divide by the sample size, and that's going to give us like the average deviation from the mean. Okay, so in a nutshell, that gives you some explanation for where this formula comes from. And to calculate it in practice, you take a value, subtract the mean value, square it, add them up for all of the values in the data set, divide by the sample size minus 1, square root, and it gives you the standard deviation. We're going to look at an example now, so hopefully this will become a little bit more clear. And there's a video associated with this where we first take the data set, make a box plot, look at the variation that way, and then go through the standard deviation calculation. I should note before I get into these details that in Excel you can also just calculate the standard deviation with a formula. There's a special formula for calculating standard deviation, so you don't have to go through this every time. But I wanted to go through it kind of the hard way to give you a sense of where it comes from, what it means, what it's doing, what that formula actually represents. So the example I picked was Michael Jordan in the 1993 NBA playoffs. So I'm a huge basketball fan and love to look at basketball statistics. 1993 is kind of prime era for me. Remember those playoffs very well. And Michael Jordan was amazing. So I wanted to look in more detail. I think this was his probably statistically best playoff performance. In those playoffs, he played 19 games. So our sample consists of these 19 games. So this is our sample. And so each game we would consider a subject. And the data that we're pulling out from each subject is Michael Jordan's points in that game. So game 1, 35 points. Game 7, 31 points. So this is the data set essentially. And then the other stuff here we'll get to in a second. So you could say, well, how much did Michael Jordan average in the playoffs? And we know how to calculate that. It turns out it's 35.1. But another additional question that we can throw on top of that is, well, how consistent was his performance? Was he consistently amazing throughout the 1993 playoffs? And to look at that, we need to think about the variation in the point totals. Now you can kind of scan it over and see some differences, like, okay, well, there was an 18-point game here, but then there's a 55-point game here. But overall, how do you take a data set like that and figure out how much variation was there on average? Okay, so the standard deviation is a measurement that will tell us some of that information. And what you do is you calculate the squared deviation for each of the point totals, for each of the data points. So for the first one here, what you do is take the value of 35, subtract the mean value, so 35, 35.1, take the difference and square it. That's what goes in this column. So 35 minus 35.1 squared gives this. There might be some rounding here, so if you do this and it doesn't come out to exactly 0.003, that you might be wondering, well, why doesn't it come out exactly to what my calculator is saying? These numbers are all rounded to 3 decimal places, and this is rounded to just 1, so there might be other digits here that are not shown. Okay, so we do that for every point total, every data point, calculate the deviation squared, and then the next step is to sum them all up. So these all get added up. So every number in this column gets added up and sums to 1,747. Okay, so we've got that sum. And then to get the standard deviation, you divide by n minus 1. So the sample is written here, 19. Minus 1 would be 18. So we divide this number by 18, take the square root, and it comes out to 9.9, or about 10. So then a more complete answer to how Michael Jordan performed in the 1993 playoffs is that he averaged 35.1 points per game with a standard deviation of 10, meaning that most nights, most games, his point total was in the 25 to 45 range. Okay, so 25 to 45 points is a rough estimate of where most of the data fell. And if you look through, that should check out, right? Most of the data falls in that 25 to 45 range. Not all, right? It's important that it's not all, so it's not estimating the range. It's just on average, how much do the data vary from the mean? Okay, so let's get to a little bit more on the interpretation of standard deviation. There's a rule, a quick rule of thumb rule, that says the standard deviation is approximately the range divided by 4. In the spreadsheet, I talk a little bit more about this, and we calculate it for the previous example. You can see that it does work out. But it gives you a quick way to assess what the variation is. So range over 4 is a much quicker formula than the square root of sum of deviation squared, etc. And with that, then to get to the bottom of the data set, you can take the mean and subtract 2 of the standard deviations. So in the previous example, if you do the numbers, it works out that the highest and lowest would be 53.6 and 16.6. So minus 2 standard deviations plus 2 standard deviations. And if you compare to the actual values here, I think the minimum was 18 and the maximum was 55. So it doesn't work out too badly at all. You get a reasonable answer just from this. Okay, now this is helping us interpret the standard deviation because it's giving us a sense of what it means. All right, the standard deviation is about a quarter of the range. Right, so you take the beginning to the end point of the data set. A quarter of that range is your standard deviation measurement. So if you go half of the, think about it. So you think about it into quadrants, into fourths, right? So you've got your range from here to here, and you divide it into 4 chunks, right? And you're at the middle. You're at the average or the mean value. If you go a quarter to either side, right, you're going from like here to here. If you go 2 standard deviations, it's taking you to the end. Later on, we'll talk about normal distributions. Actually, that's the next lecture, is normal distributions. And we'll see that a way of thinking about this is that 2 standard deviations gets you about 95% of the data. So for now, you can think about it as just about all of it. So just about all of the data will fit within 2 standard deviations on either side of the mean value. Okay, and so that's a helpful tool. Quick recap. Okay, so we've talked about variation in 3 ways: range, box plots, and 5-number summary, and then standard deviation. Now, range is a quick tool, and as we've seen here, it can be useful for thinking about it, but it's very susceptible to outliers. Median, if that's your measure of center, you probably want to make box plots and look at the 5-number summary. Or mean, when mean is your appropriate measure of center, then the standard deviation is a good tool. And you can calculate it from this formula. Okay, I would only ask you to do that either when you have Excel or when you have a small number of data points. So it would be cruel to give you 100 data points and say to calculate this formula by hand. I would never do that myself, and I wouldn't ask you to do that either. But I want you to be able to calculate with a small number of data points what this formula gives you, plugging in, adding up the deviation squared, etc. But then also to interpret what it means, what it's telling you, which is that most of the data is going to be within 2 standard deviations. So it's measuring how much spread there is, how much variation in the histogram, in the distribution.